All right, so today we're going to talk about equilibrium in aqueous solution. So if you remember, an aqueous solution is a solution where the reactants and products are all ionic solutions. And if you remember, ionic solutions have a certain concentration. They have a certain amount of solute per solvent, which is molarity, or moles over liters. And in this unit and from now on, we're going to start talking about molarity in terms of brackets. So if you see something in brackets, that means molarity or concentration. Okay, so if we have an equilibrium reaction like this one, where AA and these are all aqueous solutions in our equilibrium reaction. We can calculate something called the equilibrium constant, Kc. K is an equilibrium constant. C means concentration. It's an equilibrium constant based on these concentrations, these molarities. And Kc is equal to the concentration of the products to their power, which is the coefficient in front of them. And then divided by the concentration of the reactants raised to their powers, which is their coefficient. Equilibrium constants are temperature dependent, which means if you change the temperature, you'll have to calculate a new equilibrium constant. Kc values do not have units. They're just a number of value. And what they're going to tell us is a large Kc value, greater than 1, tells us that this equilibrium lies to the right. So when all is said and done and the rate of the forward equals the rate of the reverse, it's reached equilibrium. There's more product than reactant if K is big. So if K is greater than 1, at equilibrium, products is greater than reactants. The larger K is, the more products versus reactants you have at equilibrium. If K is less than 1, products is less than reactants. These are what we say lie to the left. Whenever you reach equilibrium, you haven't made very much product. You've made more reactant, or you've stayed on the reactant side. These only have aqueous aqueous concentrations. You would never include a solid or a liquid in this because that concentration is going to be like 1, basically. Questions so far? Okay. Okay, so when equilibrium has been established, we are going to use something called an ice table, and we'll talk more about that in a second, to find concentrations at equilibrium. So number 1, consider the following reaction where butanoic acid reacts with ethanol to produce the ester ethyl butanoate and water. In 3 separate experiments, all at the same temperature, equilibrium was achieved, and then the following data were collected. In each experiment, calculate the equilibrium constant and comment on the values. Okay, so we have for this whole reaction, K equals the concentration of water, or number of moles of water, I guess is what we should say, times, let's just label these A, B, C, D. Moles of D, moles of C, divided by moles of A times moles of B. And it's balanced so it would just be 20 times 20 divided by 10 times 10, which is 4, at that temperature. Oh, all at the same temperature. Okay, so in this one, it would be 40 times 10 divided by 20 times 5, which is 4. And then the last one would be 12 times 10 divided by 30 times 1, which is 4. So if they're all at the same temperature, changing the moles of reactant, 10 and 10, 5 and 20, 30 and 1, does not change your equilibrium at the same temperature. As long as temperature is constant, your K is going to be constant. It's going to wind up and even itself out to where the equilibrium constant is always the same at the same temperature. So when we start with 10 and 10, we wind up with 20 and 20. If we start with 5 and 20, we wind up with 10 and 40. So the equilibrium is always going to adjust based on your moles or concentration of whatever you put in. That's what's going to determine your equilibrium constant. Questions about this? Do you all see here that these are gases and I used moles instead of molarity? You're allowed to do that, and we'll talk more about that next time. But moles and liters are kind of the same thing in this case. Okay, let's keep going. Using the reaction in the KC calculated in question 1, calculate the number of moles of each substance present at equilibrium when 1 mole of butanoic acid and 2 moles of ethanol are mixed at the same temperature. Okay, so this is where we use something called an ICE table. An ICE table stands for initial change and then equilibrium. So your ICE table is going to be, it's just a problem-solving method. It's not anything necessarily chemistry related, but it's a way that we can solve problems. And in this case, you always write out your reaction, whatever the reaction is at the top, and then you write initial change equilibrium, ICE, and you put in your values that you're given. So for any equilibrium reaction, you're given either reactants or products. You can even start with a little bit of product and some reactants. Doesn't matter. But you fill in the table. In this case, we were told that we were given 1 mole of butanoic acid and 2 moles of ethanol. So I put those in. I did not start with any product. If it doesn't tell you that you started with product, you assume you don't start with product. So those start out as 0. Okay? Then my change, I'm going to lose reactant. And because it's a 1 to 1 to 1 to 1 ratio, however much reactant I lose is how much product I will gain. Does that make sense? It's a 1 to 1 ratio. If it wasn't, then I would have to deal with that, and we'll talk about that later. Then, at equilibrium, I'm going to show that this is 1 minus x. This is 2 minus x. You just take the initial minus the change to get the equilibrium value. 0 plus x is x. 0 plus x is x. And then at this point, I would fill in. I knew, so K is the concentration. We label these A, B, C, D, or the moles. It would be C times D over A times B. In the problem before, we found out that K equals 4. C is X. D is X. A is 1 minus X. And B is 2 minus X. Simplify x squared. And then here, this is where chemistry kind of gets trickier. Do you all know how you deal with this? You FOIL, right? So I would FOIL and I would get 2 first, minus 1x minus 2x is minus 3x plus x squared. And I would wind up with this equation where I'm expected to solve for x. You will not be expected to do a quadratic equation on the AP test. This is as far as you would have to go, or we're going to learn later about some things that you can cancel out. Now, you take college chemistry, you might have to do the math that deals with that. But in AP, because of time constraints and because there are some calculators that can do this and there are some calculators that can't do this, they're going to give you some tricks, and I'll give you tricks as we go. But for now, just know that this is where you would stop, and you could solve for x, and x would give you your concentrations at equilibrium. It is working backwards, or your number of moles at equilibrium. Do you have questions for me? Okay, let's try one more. I changed my mind. Because of the way that the schedule's working, I'm going to work this tomorrow. So you'll see the video of this tomorrow. All right, that's it. I'm done for today.